In this video, we are going to discuss matrices, VSAQ's continuation. 11th question, define symmetric matrix and give an example. Solution, definition of symmetric matrix. Definition of symmetric matrix. A square matrix capital A is said to be symmetric matrix. A square matrix capital A is said to be symmetric matrix if A transpose is equal to A. See, this is the definition of the symmetric matrix. A square matrix capital A is said to be symmetric matrix if A transpose is equal to A. For example, here, suppose the matrix A is equal to, so general matrix of 3 by 3, suppose A11, A12, A13 and A21, A22, A23, A31, A32, A33. So this is the square matrix of order 3 by 3, general square matrix of order 3 by 3. Suppose A is a square matrix, A is a symmetric matrix. Suppose this is a square matrix already. Suppose A is a symmetric matrix. So here, A12 is equal to A21 and also A13 is equal to A31. So A32 or A23 is equal to A32. See, this is the condition. Suppose if A is a symmetric matrix, so that's why we can give the example here. So the example of symmetric matrix is capital A is equal to, as per this, so A12 is equal to, that means A12 means here the element, suppose here if you take 1, A11, here if I take 2, so A12 is equal to A21, both are the second row first element, A13, that means suppose if I take here 4, A13 is equal to A31, both the elements are same, and A23, that means second row third column element, that means if I take here 5 and A32, that means third row second element, that is here 5. Rest of the elements you can take anything, suppose see here. So A12 is equal to A21, so A13 is equal to A31 and A23 is equal to A32. So like this, any example you can give for symmetric matrix. For symmetric matrix you can give like that any example by taking the elements. A12 is equal to A2, that means A12 means first row second column element is equal to second row first column element, and A13 means first row third column element is equal to A31, that is third row first column element, and A23 is equal to, that means second row third column element is equal to third row second column. Like that, if you take any elements, the rest of the elements you can take other elements. Like that you can give the example. Here A12 is equal to A21 is equal to here, so 2, A13 is equal to A31 is equal to, so here 4, so A23 is equal to A32 is equal to here 5. See, like that you can give. This is not compulsory. You can take any elements are equal like this. The rest of the elements here you can take any other element. That means you can observe that clearly principal diagonal elements you take any other elements, and these elements you can take the equal as you wish. And also we can say the examples. This is suppose example 1. See here, zero matrix identity matrix, that means unit matrix. So unit matrix, zero matrix or unit matrix. So diagonal matrix, see here, diagonal matrix. So matrix are always symmetric matrices. are always symmetric matrices. Or symmetric matrix. So that's why you can give the example here. Any zero matrix is also a symmetric matrix. You can give the example. So unit matrix of order 2 or order 3, you can give the example for symmetric matrix. And diagonal matrix, any diagonal matrix except the diagonal elements, remaining all elements are equal to 0. That like that also you can take the example for symmetric matrix. Like this we can say the definition of the symmetric matrix is a square matrix capital A is said to be symmetric matrix if A transpose is equal to A. That means transpose of matrix A is always is equal to the same matrix. So that's why we can say that we can define the symmetric matrix is A transpose is equal to A. The next question is 11th question. Define skew symmetric matrix and give an example. Skew symmetric matrix definition. A square matrix capital A is said to be skew symmetric matrix if transpose of A is equal to negative. That means additive inverse of A. Additive inverse of A means minus A. So A transpose is equal to minus A. Suppose for example here, so we have the general matrix. Suppose we have capital A is equal to the general square matrix A11, A12, A13, A21, A22, A23, A31, A32, A33. So here to give the example of this is here clearly to say that, so if A is a skew symmetric matrix, so then A12 is equal to minus A21. A13 is equal to minus A31. And also A23 is equal to minus A32 in any square matrix. Then we can say that capital A is a skew symmetric matrix. If this is a capital A is a skew symmetric matrix, so then we can say that so here A12 element is equal to minus A21, A13 element is equal to minus A31, A23 is equal to minus A32. So that means to write the example of this is, so example we can take that, see suppose let A is equal to what I told you here in A11, you write any element. That means you have to observe that in the skew symmetric matrix the principal diagonal elements are always equal to 0 only. Here 0 and A12 is equal to minus A21. A12 if you take 1 minus A21 you take minus 1, and A13 is equal to if you take 2 and here you take minus A31 here, so that's why minus 2. So and again here A23 suppose if you take 3 and here A minus A32, so that means minus 3, and rest of that means particularly in the skew symmetric matrix the principal diagonal elements are always equal to 0, So that's why like this we can say that here A12 is equal to minus A21, A13 is equal to minus A31, A23 is equal to minus A32. Like that you can give number of examples. So here which is a skew symmetric matrix, and also clearly here you can write that here. So here A12 is equal to minus A21 is equal to here 1, and A13 is equal to minus A31 is also is equal to here. So this is 2, and you can observe that A23 is equal to minus A32 is equal to here, so 3. So like that we can A23 is equal to minus A32. So that's why like that you can observe that here. So A12 is equal to minus A21, A13 is equal to minus A31, A23 is equal to minus A32. You can observe in the matrix A also. Clearly you can write the example like this. The next question is 13th one. If A is equal to 2 minus 4 minus 5 3, then find A plus A transpose and A into A transpose. It is also very important. So in the given problem, so given that capital A is equal to, matrix A is equal to, so 2 minus 4 minus 5 3. See what we have to find here, A plus A transpose. So now I am finding A transpose. A transpose is equal to, see first row writing into the column 2 minus 4 and second row writing into the column. Transpose means the rows interchanging into the columns. So we get A transpose. Then what we have to do? A plus A transpose. So therefore A plus A transpose is equal to, so matrix A is 2 minus 4 minus 5 3 and plus A transpose, that is 2 minus 5. So minus 4 3 here. So which is equal to, the corresponding elements are adding here. So 2 plus 2, the corresponding elements, and minus 4 and plus minus 5. So and here corresponding elements are minus 5 plus minus 4 and here corresponding elements are, so 3 plus 3. So we get here which is equal to 2 plus 2 is 4 and minus 4 plus into minus is minus 5, which is minus 9, and minus 5 and plus into minus is minus 4. So minus 5 minus 4 is minus 9 and 3 plus 3 is 6. So clearly we get A plus A transpose is equal to 4 minus 9, 6. Similarly we have to do that. A into A transpose. Now A into A transpose is equal to, matrix A is 2 minus 4 and minus 5 3. So which is multiplying with the A transpose, that is 2 minus 5 minus 4 3 here. So which is equal to, we get, so multiplying first row first column, so that is 2 into 2, immediately write plus and minus 4 into minus 4 here, minus 4 into minus 4, first row first column multiplied, first row second column, that is 2 into minus 5 here, 2 into minus 5 plus immediately and minus 4 into 3 here, first row second column multiplying here, minus 4 into 3 here, minus 4 into 3, and similarly here second row first column, writing in the place of second row first column here, minus 5 into 2, minus 5 into 2, immediately plus 3 into minus 4 here, 3 into minus 4, and also here, so second row second column multiplying, minus 5 into minus 5, so minus 5 into minus 5, again immediately plus, so 3 into 3 we can write, 3 into 3 like this. So second row second column multiplied, so we get here which is equal to, if you simplify, this is 4 and plus here 4 into 4 is 16, and here minus 2 into 5, that is minus 10, and here minus 4 into 3, that is minus 12, and here minus 10, 5 into 2, minus 5 into 2, and here minus 3 into minus 4, that is minus 12, and this is minus into minus is plus 25, and here plus 9. So clearly we get here, if you simplify, so 16 plus 4, that is 20, and here minus 10 minus 12, that is minus 22, and minus 10 minus 12, which is minus 22, and here 25 plus 9, this is 34. So like that we get A into A transpose is equal to 20 minus 22 and minus 22, 34. We get both are 2 by 2 matrices only here. Columns of the first matrix is equal to rows of the second matrix. So that's why multiplication is possible. Resultant matrix order is also 2 rows and 2 columns here. So that's why resultant matrix order is also we get 2 by 2 like this we can do. So the next question is, if A is equal to minus 1, 2, 3, 2, 5, 6, 3, x 7 is a symmetric matrix, then find x. See what is given here. Given that the matrix A is equal to minus 1, 2, 3, 2, 5, 6, 3, x 7. See, and also what is given here, since capital A is a symmetric matrix, is a symmetric matrix. See, we know that as per the definition of the symmetric matrix here, so A12 is equal, that means first row, second column element, A12 is equal to A21, we know that. And also, so first row, third column element, that is A13 is equal to, so third row, first column element, see here, third row, first column element. First row, second column element is equal to second row, first column element. So A13 is equal to, so here A31. And also similarly here, so we know that A23, that means what? Second row, last column element, so is equal to, so third row, second column element, that means what? A32. See, here clearly if you observe in the matrix, A12 is equal to A21 is equal to 2 only, both are. So A13 is equal to A31 is equal to, both are 3 only here. So as per that here, so A23 is equal to A32 only. So that's why therefore here we can take that to find the value of x. So A23 is equal to A32 you can take. So that means what? Which is implies A23 is equal to what here? 6, which is equal to A32 is what here? X. So therefore clearly we can write, so the value of x is equal to 6. Like this you can find simply, if the given matrix is a symmetric, the value of x. The next question is, if A is equal to 0, 2, 1, minus 2, 0, minus 2, minus 1, x 0 is a skew symmetric matrix, then find x. See here, given that matrix A is equal to 0 to minus 1, 0 to 1 here, and minus 2 minus 2, 0, minus 2, and minus 1, x 0 here. See, and also what is given, so capital, since capital A, matrix A is a skew symmetric. So is a skew symmetric matrix. See, clearly we know that when it is a skew symmetric matrix, we have the condition. What is that? So A12, that means first row, second column element is equal to minus A21. See here, both are 2 only here. A12 is equal to, A12 is 2, A21 is minus 2. So that's why both are same only. And also here, that means with opposite sign. And again here A13, that means first row, third column element is also is equal to minus A31. So A13 is equal to minus A31. So you can observe here clearly. And also here A23 is equal to minus A32 here. A23 is equal to minus A32. We have these conditions actually. But here, which condition is applicable to find the value of x? A23, that is minus 2, which is equal to, so minus A32. That means what here? Minus A32 is x. So both sides see minus gets cancelled. So simply you can write x is equal to 2. So like this we can find, if given matrix is a skew symmetric, And also you can observe that in the skew symmetric matrix, the principal diagonal elements are all equal to 0. So like this you can find the value of x. The next question is, if A is equal to cos alpha, sin alpha and minus sin alpha, cos alpha, then show that A into A transpose is equal to A transpose into A is equal to I. So given that matrix A is equal to here cos alpha, sin alpha and minus sin alpha in the second row and cos alpha. See, we know that transpose of A. What is transpose of A? A transpose is equal to. So just writing first row into the first column, that is interchanging the column into or row into column. Right? Cos alpha, so sin alpha, row writing as a column. And second row writing as column, that is minus sin alpha, cos alpha. So we get the A transpose, see here. So interchanging the rows into columns, we get A transpose. Now multiplying A into A transpose is equal to. So both the matrices multiplying here. So this is cos alpha, sin alpha and minus sin alpha, cos alpha in the second row. So and multiplying this is with so cos alpha minus sin alpha and here sin alpha, cos alpha. See, when you multiply here, see first row, first column you have to multiply. That means cos alpha into cos alpha into cos alpha, that is cos square alpha, immediately plus, and sin alpha into this sin alpha, that is sin square alpha. See, first row, first column multiplied. First row, second column elements you have to multiply. Cos alpha into minus sin alpha, that is minus cos alpha, sin alpha. So again immediately plus. So sin alpha into second element, sin alpha into cos alpha, that is sin alpha, cos alpha. Similarly, second row, first column. So minus sin alpha into cos alpha, that is minus sin alpha into cos alpha, plus here this is minus sin alpha into cos alpha, immediately plus cos alpha into sin alpha, that is it. So cos alpha into sin alpha. Again second row multiplying with the second column. See, minus sin alpha into minus sin alpha. Minus sin alpha into minus sin alpha. Minus into minus becomes plus. Sin alpha into sin alpha, that is sin square alpha. Again you have to put the plus immediately. So cos alpha into cos alpha, that is cos alpha. So cos square alpha, that is cos square alpha. Cos alpha into cos alpha, cos square. See, observe here. So these two terms are same only, but opposite in sign. Sin alpha cos alpha plus and minus sin alpha cos alpha with minus gets cancelled. And also here, so plus cos alpha sin alpha minus sin alpha cos alpha gets cancelled. We know that cos square theta plus sin square theta is equal to 1. So cos square theta plus sin square theta is equal to 1 we have. Same like that, cos square alpha plus sin square alpha is also is equal to 1. A into A transpose is equal to, we get here 1, and that second element is both are gets cancelled, 0 here and here 0, and here we get again 1, so which is equal to I. So that's why we get A into A transpose is equal to. So that implies A into A transpose is equal to I. Similarly, suppose if you take A transpose into A, so which is also is equal to, first writing A transpose, that is cos alpha minus sin alpha, and here so sin alpha cos alpha, this is A transpose. So A transpose multiplying with matrix A, so that is cos alpha sin alpha, and here minus sin alpha cos alpha multiplying this is A. Then what we get? See, again first row, first column multiplying. Cos alpha into cos alpha, that is cos square alpha, plus immediately. So minus sin alpha into minus sin alpha, that is plus sin square alpha. Minus into minus is plus only here. Again first row, second column. cos alpha into sin alpha, that is cos alpha sin alpha. Cos alpha sin alpha, immediately plus, but here minus sin alpha into cos alpha. So that is minus sin alpha cos alpha. Minus sin alpha cos alpha. Again here second row, first column multiplying. Sin alpha into cos alpha, that is sin alpha cos alpha. Sin alpha cos alpha. Again cos alpha into minus sin alpha, that is plus minus sin alpha cos alpha or cos alpha sin alpha. See, observe here. Again second row, second column multiplying. Sin alpha into sin alpha, that is sin square alpha, plus. So here cos alpha into cos alpha, that is cos square alpha. So here if you observe, this is also minus and plus, this is minus plus, gets cancelled, there we get 0 only. Same like this property, cos square theta plus sin square theta is equal to 1. So A transpose into A is also we get, so 1 0 0 1, so which is equal to I only. So therefore here that implies A transpose into A, suppose, which is also we get I only. So therefore finally we can write A into A transpose is equal to A transpose into A is also is equal to I. So like this we can prove.